The topic of this video is error propagation. While error propagation isn't a technique which is unique to chemistry, I've become quite familiar with it as per the weekly lab reports for Chem 211. In simplest terms, no measurement or quantity is exact. As an example, while 3.583 grams may sound like an accurate measurement, there's always another level of precision, another decimal which could be measured. Thus, we'll never actually obtain and use the true value in our calculations. So let's imagine we're doing an experiment where we take these 3.583 grams of some chemical, react it with another compound, dilute the product, distill it, and crystallize it. At each step of this process, there are more and more measurements which don't 100% accurately represent the real values, hence the idea of error propagation. As these changes accumulate, error propagation is the technique which tracks how the overall uncertainty grows. So this example, we cover basically error that comes from the equipment. Equipment's not perfect, but there is a few different types of error that can commonly occur during your experiment. Systematic error. These errors are ones which have some level of consistency over multiple measurements, and they all skew in the same direction. So imagine you're tearing a scale and you accidentally forgot your 10-gram pen on the scale. Now, every single measurement until you calibrate it will be 10 grams lighter than they should be. A consistently wrong measurement. There's also random errors. Random errors, unlike their systematic counterparts, they're like dice rolls. They can go either way. They're caused by unpredictable fluctuations. Maybe it's slight variations in your hand movement when titrating, or minor changes in ambient conditions. These errors are particularly tricky because they can be hard to predict and control. But here's the catch. They often average out over multiple measurements, which is why repeating experiments is so vital. Finally, there's human error. Yes, we humans are not infallible, especially in a lab setting. Whether it's misreading an instrument, spilling a sample, or simply making a calculation mistake, human error can introduce significant inaccuracies. The key to minimizing this? Practice, attention to detail, and double-checking your work. Now, depending on what calculation you're doing, error propagates differently. Think about it. If you aren't sure if the unknown variable x is equal to 2 or 3, but you know it's probably one of these, then the answer to the operation 10 to the power of x will have much more variability in the incorrect outcome than something like 10 plus x. Thus, the formulas used to propagate error must reflect this. So on screen are the error propagation formulas for the common operations you might see in chemistry. And as you can see between them, there's some distinct differences. For products or quotients, the combined error is the sum of the relative errors of each variable. This formula reflects the proportional impact of each variable's uncertainty on the final result, regardless of the operation being multiplication or division. With logarithmic functions, the error is linked to the relative error of the variable. Logarithms compress the scale of values, meaning that even small errors in the original measurement can significantly impact the logarithmic result. And then finally, for exponentiation, as we explained in the example earlier, the deviations will be even greater. And there are various formulas for various operations, but on the screen are just the most common ones. So, as my fellow ISP students remember, in this class we went over some statistical information and topics. Well, in chemistry, especially in the field of error propagation, statistical methods are also very useful. I will briefly explore how basic statistical concepts are essential in error analysis, particularly in the context of chemistry experiments. These tools are not just about numbers. They help chemists understand, quantify, and manage the uncertainties in their measurements. So first, we must cover standard deviation and variance in chemical measurements. Standard deviation in chemistry labs is crucial for assessing the precision of repeated measurements like the mass of a compound or the volume of a solution. A low standard deviation in repeated titrations, for instance, indicates consistent results, whereas a high standard deviation suggests variability that needs addressing. Variance gives a broader view of the spread in data. Like the variance in concentrations obtained in multiple samples, it helps in comparing the consistency across different sets of chemical experiments. So then what is the application in chemical analysis? Well, understanding standard deviation and variance is vital for chemists to evaluate the reliability of their experimental results. For example, when determining the purity of a substance, the standard deviation of multiple measurements can indicate the method's reliability and potentially tell you if the experiment needs adjusting or if it provides a final product which is to the needs of the experiment and its purity requirements. There is also something known as confidence intervals. So to understand confidence intervals in the realm of chemical analysis, a confidence interval provides a range in which we can expect the true value of a measurement to lie. For instance, if analyzing a new compound, a 95% confidence interval for its melting point would indicate that the range within the true melting point is likely to be. So when it comes back to error propagation, in reporting your chemical research, including confidence intervals with mean values is critical. It shows the extent of uncertainty in measurements like reaction yields or compound concentrations, providing a clear picture of the data's precision. And by applying these statistical methods, chemists can refine their experimental techniques, especially when dealing with complex reactions or when precise measurements are crucial, such as in the pharmaceutical synthesis pipeline. Knowing the standard deviation helps in optimizing experimental conditions like temperature control in a reaction to achieve a more consistent result. Confidence intervals are particularly important in research and development in the chemical industry, where understanding the precision of measurements can impact the scalability, reproducibility of chemical processes. So, to conclude this section of the video, I want to mention why all of this is important to the field of chemistry. In the realm of chemistry, where the mysteries of molecules and reactions unfold, an invisible yet essential partner plays a pivotal role: mathematics. Imagine a chemist in a laboratory, meticulously measuring substances and conducting experiments. Each experiment, whether it's a volume in a beaker or the mass of a compound, depends on absolute precision. Mathematics in this setting is not just a tool, but a guardian of accuracy. It guides the chemist in quantifying uncertainties, ensuring that the purity of a reaction or the concentration of a solution is not just an estimate, but a figure backed by mathematical certainty. The precision is the foundation upon which the trustworthiness of pharmaceuticals, environmental analysis, and new material development rests.
21, can you propagate for me? Can you whip up a rich batch for me? And 21, can you test something for me? Drop some knowledge like a chemist app for me. Then 21, can you solve something for me? Can you break down the compounds for me? Not 21, propagate for me, yeah. Do you think 21, propagate, yeah, for me?
White crystals in the flask, precision means a lot, never mix without a plan. That's how you go flop. I calculate in mode, I do that math a lot. She sees the reaction, says the mix harder than the blot. All my trials accurate, result in never bluffing. If my trials ain't precise, then their data's not worth nothing. You ain't ready with the data, they don't fudge it. I know it's complex, baby, but can you judge it? I'm a chemist, mix it up, no panic. I'll solve a complex problem, make it vanish. I might track the reaction, get the graph to manage. Don't call me when I'm busy, baby, I'm in my labby. Lab coat on me, goggles on. Always in my data, precision ain't free. Why some scientific results, but that ain't me. Life alive like a...
Thank you guys. I hope you enjoyed my video about air propagation. Everyone else's video was amazing, and that's all.